WPA3 and OWE Wi-Fi security. And with us today, our special guests, Tuomas Aaltonen, CWNA CWSP, and our solutions engineer for EMEA. He is located in Helsinki. For those of you who are dialing in from overseas, we'll drop a LinkedIn for Tuomas. We'd love for you all to connect. If you haven't met over the years, Tuomas has been with 7Signal for about 10 years. The company was founded in Helsinki, Finland, and he was part of the original crew that brought 7Signal to life. Also with us today, Heather Dremel, with us each and every week, our digital marketing manager, and of course, Jim Vada, our chief wireless officer. So Tuomas, I'm gonna hand the controls over to you, and we'll get started.
All right.
And they're coming right now. And we can see your screen. You're good to go.
That's good. Yeah, a little bit about myself. Like Don already mentioned, I've been in 7Signal for 10 years now. Joined the company in the early phase, and for the last 4 or 5 years, I've been in solutions engineer role here in EMEA. I live in Finland, Helsinki, which is known from its thousands of lakes and forests. And I hold the CWNA and CWSP certificates, and just recently passed the CWSP certificate, and that's kind of led me to today's topic. All right, so agenda for this webinar, we'll look into the WPA2 first. It's important to understand how that works before we go into the WPA3 and why that is needed. Then we're gonna talk about WPA2 weaknesses, what's changed in WPA3, and then the second part is about the enhanced open or the OWE, and then the client support for the opportunistic wireless encryption. Just an overview of the WPA2, and of course everyone knows what that is. It's been the kind of main security program since 2004, and it's a security program by Wi-Fi Alliance, and the WPA2 personal uses a pre-shared key in encryption key creation process. And there are 2 variants. There's WPA2 personal and then WPA2 Enterprise, which enhances the security a bit by using EPA authentication, for instance. Some weaknesses there, just a few of them are the key reinstallation attacks. This became known in 2018, really, where the attacker can exploit the 4-way handshake that happens during the WPA2 process. And we'll look into that in the next slide a little bit. Offline dictionary attacks that are possible. So the attacker can use that to try to attempt to guess the correct password for the PSK network. And then eavesdropping is easy for, well, not easy, but it's possible for the attacker to use, for example, in man-in-the-middle attacks and denial of service attacks. A little bit about the weaknesses. Like I mentioned, the key reinstallation attack, which became common, well, not common, but known for the public in 2018. It's basically a man-in-the-middle attack where the attacker is going to resend the message tree in the 4-way handshake to the client until it can get enough information about the keys to actually compromise the keys used between the client and the access point. So that's kind of a weakness in the 4-way handshake process, and also especially in the when that pre-shared key and how that is derived from the master session key, but we'll look into that in the next slide. Offline dictionary attacks. So basically, if you capture enough information about the WPA2 authentication process, the attacker can just, use that file. They don't need to be physically on site anymore. They can just try to guess the correct password, either with, offline the dictionary attack, or just by using a brute force. And then management frames that are not protected, or they are sent unencrypted over the air. This can be used to, for instance, in the authentication attacks, where you force the already associated and authenticated client off the network, and then try to force that client to another access point, to a rogue access point that the attacker is using. Plus, the WPA2 doesn't have really, or the WPA3 will give protection also for the simple password that you see in this image. That are those, typically known weak passwords. So WPA3 can give a better protection for those. Just a little bit about the brute force attacks and the offline dictionary attacks. I wanted to show this. I thought it was kind of interesting to see the impact of, the password length. So for instance, if you look at the this picture here, you can see, for instance, that WPA2, the minimum password length is 8 digits, and if you use only the alphabeticals, the lowercase and uppercase alphabeticals from A to Z, it's about 1.6 years for a system like this, which can go through 1 million guesses per second, to guarantee that the password gets compromised. And of course, if the system is lucky, there's a 50-50 chance that it will crack that password already in 7 or 8 months. But then if you look at the time, how much it increases when you add one more digit there, with 9 digits you are at 88 years, 10 digits you are at 4,500 years, etc., etc., and 12 digits is already, I believe that's 12 million years. So you see that exponential growth by just adding 1 digit there. So I thought this was interesting to show, and I dropped the source there if you want to check out this calculator, where you can change these parameters. You can change the password cracking speed and also the processing elements. Just an overview of the WPA3, which was released by Wi-Fi Alliance in 2018. It's mandatory in Wi-Fi 6 or 11AX. And all of the new Wi-Fi certified devices, they need to be in compliance with the Wi-Fi WPA3 since July 2020. The user experience remains same, so a password is shared between the client and the access point. And of course, then there's the enterprise mode as well. So there's the WPA3 Personal and WPA3 Enterprise. But the biggest difference actually is between the WPA2 Personal and WPA3 Personal. So the benefit of WPA3 Personal is more greater than what the Enterprise option gives. So this preset key is replaced by simultaneous authentication equals. That's where the SI comes from, which is using Dragonfly key exchange. I've added the RFC number there if you want to look into how the Dragonfly key exchange works, but we'll check that on the later slides also. And then there are transition modes, for instance, that you can on one SSID support both, both clients that are not able to use WPA3, you can still have an SSID where WPA3 clients would be using WPA3, and the clients that don't support would still use WPA2. And for the enterprise, there are two variants: just the standard WPA3 Enterprise, and then another mode which is called 192 WPA3 Enterprise 192, which uses even stronger security algorithms and increases the encryption key length to 192 bits. And another thing is WPA3 requires the support for the protected management frames. So these are the benefits over the WPA2. Of course, it's going to tackle the vulnerabilities in the WPA2. So these key reinstallation attacks are not possible. Offline dictionary attacks are not possible due to these enhanced algorithms, and it provides better protection for these simple passwords. Another thing what it provides is forward secrecy. This is a term used when for instance, if the key is compromised, the past and future session are still safe. And then due to using protected management frames, it makes it harder for passive eavesdropping. So you cannot use, for instance, the deauthentication method to force a client to authenticate onto a rogue access point. Here's something about the four-way handshake. We need to understand the keys part of it. The first one is the most important one, which is the pairwise master key. And in WPA2 PSK, this gets generated from the password itself. Okay, so that's important to understand. And then from this key, from this PMK, during the four-way handshake, a PTK is created, pairwise transit key. And this is an encryption key between the client and the access point to encrypt the unicast traffic. And then there's a third key called GTK, or group temporal key. And this is used to encrypt the broadcast and multicast traffic on the same session. And then a few other things that are kind of relevant to understanding this process. These A nons and S nons are just used in this process to actually derive these and install these keys. And I've dropped the formula there at the bottom, how this pairwise transit key is actually created by using the pairwise master key, and these other information that's sent between the client and the AP during the four-way handshake. Here's a look at the frame exchange between access point and the client, and this is the WPA2 PSK. It's different from the WPA2 Enterprise. It's good to remember that. So, but the kind of weak part here is that this PMK, the pairwise master key, is generated from that password. And the keys then are derived during that four-way handshake. The client derives the PTK after the authentication nonce, and then the supplicant sends the nonce message to access point. It derives the pairwise transit key, generates the group temporal key, and then both of them install the PTK and acknowledgements, and that's where the encryption starts. I wanted to show here on a packet level in a Wireshark how this works. The purple frames there are the open authentication and association. The yellow part there is the four-way handshake. And then you'll see after the authentication is complete, you'll see that there's, for instance, encrypted multicast traffic. And this is without a password, so we don't know what the password is. But basically, you would only need this part, or the attacker needs this part of the frame exchange. If they can just see the four-way handshake, they can try guess what the correct password is, because that would immediately unencrypt the data. So here, if you add the key onto your Wireshark, you can see, for example, in this session, on this same machine, which has been used to capture this frame exchange between this iPhone and access point. Now, when we know the key, you can see the multicast traffic is unencrypted. And I've added there, if you want to try it out on our Wireshark, to upload these keys and how to unencrypt the data of the WPA2 PSK session. So how this is changed in WPA3 SI. So this is the simultaneous authentication equals. So instead of that open authentication, there's 4 authentication frames exchange between the access point and the client. And this first sequence is a commit message from the client to the access point, and then from the access point to the client. And after this, there's a sequence 2, which is the SI confirm message from client to AP, and then back from AP to the client. And this process is called Dragonfly key exchange. It's a cryptographic algorithm to derive this PMK. And if we just went through the previous slides on the WPA2, where the password is actually the PMK, here the PMK is generated in this Dragonfly key exchange process. Okay, so both of the client and the access point still have the password, but this password is not used anymore directly in the PMK. It's actually just pointing to an elliptic curve index, another cryptographic term, and from this random number, which comes from that elliptic curve, it does calculate this PMK. So if you look at the exchange there between the access point and the client, you see there's, for instance, ECDH group. That comes from elliptic curve Diffie-Hellman group ID. And then there's client scalar and AP scalar, which is basically just a random number used in this process. And then client and access point finite field elements. And this finite field element actually refers to this point on that elliptic curve. So once AP and the client has exchanged all this information, it can now derive this pairwise master key. Okay. And it's basically just based on zero knowledge proof. So if I know a secret word, and I know, for instance, that, well, I assume that Heather knows the secret word too. And if I'm in the same room with Heather, with Jim and Don, and I need to confirm that Heather knows the secret word, how am I able to do it without actually saying the word aloud, without Jim and Don hearing it? So that's the kind of fundamental problem that gets solved by this Dragonfly key exchange. And then after this PMK has been derived, it's followed by association request, association response, and then the same four-way handshake to derive the session keys, the PTKs and GTKs, etc. But it's important to understand in this side authentication process that each client will have different unique PMK. So, and that's different from the WPA2 PSK, where the password is basically used directly to generate this PMK. So even if the attacker would know the password, they wouldn't be able to decrypt the data between this this client and the AP. It's a dynamic key, and due to this enhanced cryptographic algorithm used in this it becomes impossible for the attacker. This commit part also includes a token which will be used to limit how many simultaneous connections can be attempted. So this is the part where the protection comes for the dictionary attacks. Okay. So we just looked into WPA2 PSK and WPA3 personal, but this is a comparison of the WPA3 Enterprise and then WPA3 Enterprise 192. And if we look at and compare it to WPA2 Enterprise, the only difference in WPA3 Enterprise is that it mandates the support for protected management frames. So all the authentication frames, you know, all the management frames are protected. Okay. So the only requirement for a client that's previously used WPA2 Enterprise is that it supports PMF, the protected management frames. You can still use the same EAP authentication methods that were used on the WPA2 Enterprise, like EAP with MS-CHAP version 2 to authenticate the user. WPA3 Enterprise 192, like the name suggests, it increases the total length of the encryption key from 128 bits to 192. There are a few requirements in that one, and it only allows use of ETLS certificates. So all these other older, not that secure, like EP, for instance, wouldn't be allowed in this mode. You can also see that it's using IS-256 instead of IS-128, and so basically it's just using stronger encryption methods than the previous version and what the WPA3 Enterprise does. But you could use this type of an I can kind of see that this would be used in some really secure networks, like a military or governmental networks, maybe, where you have really sensitive data. On a normal organization network, I would see more use for the WPA3 Enterprise. Then the second part, which is about the opportunistic wireless encryption, that's an actually interesting. I didn't know about it before I passed my CWSP course, and it's an interesting one because it's aimed to improve the privacy and security on open Wi-Fi networks without actually impacting the user experience. So everything for the user would look same, except that the data between the access point and the client gets encrypted. This is based on Internet Task Force RFC 8110. It uses Diffie-Hellman key exchange to derive the pairwise master key. It's basically based on private and public keys. As well, this requires the use of protected management frames, and there's two modes: the enhanced open only mode, and then of course the transition mode, where you would still support clients that don't have a support for the OWE or the enhanced open. So why that is needed? There are of course a lot of networks and environments where organizations offer free Wi-Fi service for visitors, for instance. And typically these innocent visitors may not always know what to do, or may not know what they are doing when they join an open Wi-Fi network. They don't necessarily understand that all that data is sent across the Wi-Fi or the wireless network without any encryption. Of course, when you are on network on open Wi-Fi, you should be always using like a VPN, for instance, to encrypt the data. But I don't think most people care or don't know that such things would need to be used to protect their privacy. So this makes these users really easy targets for these kind of attackers who may be there to listen the network traffic. So I've added how this OWA works compared to just an open Wi-Fi network. Of course, in an open system authentication, there's just 4 frames between the access point and the user device. You see the authentication and the request response, and then association, and then the data gets sent in clear text. Whereas this OWE actually adds in an extra element there. If you look at the association request there on the right-hand side, you'll see that in that association part, it negotiates this Diffie-Hellman key, which is based on those private and public key pairs, and then automatically after that, negotiated. It's followed by the 4-way handshake again, creates the PMK before that, and then 4-way handshake where it derives these session keys like PTK and GTK, and then it starts automatically encrypt data. So the user doesn't need to basically do anything. So it happens on fly, and the client and the AP just negotiates the encryption keys that will be used. Okay, this actually explains the same thing that I just told. So I'll move on to the next slide. So if you compare opportunistic wireless encryption to just WPA2, here we can see that, for instance, in OWE, the PSK is actually, the password itself is used in the creation of the pairwise master key, whereas in OWE, that pairwise master key was created in that process, that Diffie-Hellman key exchange process between the client and the AP. And it's a dynamic key, and that's kind of an way to put it, that the OWE actually might be even stronger than the WPA2 PSK due to this way how this pairwise master key is being generated. As well as, for instance, if we think about ease of use, I think many of us have been in a restaurant, for instance, asking the waitress or waiter the password of the Wi-Fi network and never got it working. Whereas OWE, for the encryption part, you don't need any passwords or anything, so you can just go ahead, join into open Wi-Fi network, and everything happens automatically. So the encryption gets created on the fly. Do the protected management frames in OWE, the passive eavesdropping is more challenging for the attacker. So those typical deauthentication methods wouldn't work in these networks where the attacker basically sends fake deauthentication frames, forces the client to deassociate from the network, and then probably try to attract the client to join it to the attacker's own rogue access point. Here's a little bit about client support. So I looked into Intel, Android, and Apple. For instance, on Intel, all the latest Wi-Fi 6, well, all the Wi-Fi 6 adapters support OWE, and all the latest Wi-Fi 5 adapters support opportunistic wireless encryption. For Android, it's Android 10 or later, but Apple iOS and Mac OS don't support it, which I find interesting. But of course, I don't know whether it's going to change or not after we start to see 6 GHz networks out there, because it's 6 GHz band only. It's going to support only WPA3 and OWE. So I don't know if Apple has plans to change that, but I guess that will happen. Then, if you want to quickly check on from your own PC, this is for Windows, not for Mac, but you can run this command on your laptop, on your Windows laptop, and this shows all the authentication cipher supports that your Wi-Fi adapter supports. And if it does support OWE, it will be on this list. Whereas in this case, there's not even a WPA3, because I took it from my home Windows laptop, which is fairly old compared to my Mac that I'm using in work. And that's actually the last slide. Let's go back to Heather and to Q&A.
Yeah, great job, Tuomas, and I'll manage the Q&A, Heather, if you don't mind. I've been looking at stuff as it's come in, and we've had a lot of good questions come in. So if anybody has another question, go ahead and drop it in the Q&A panel. First, just a comment from Anders. He says he's listened to the WBA conference yesterday, the Wireless Broadband Alliance, and they said that WPA4 will be introduced with Wi-Fi 7 in 2 to 3 years from now. So first I've heard of that. So just interesting. Not sure what the necessity of it is. Even WPA3, improves on the security of WPA2, but if you deploy WPA2 properly, it's still pretty secure. So interesting. I have to keep an eye out for that. Interesting question here, Tuomas, from Daniel. He says he's curious about the impact of OWE on airtime use. Did the management overhead problem get solved that's caused by the extra BSSIDs OWE requires?
I think that refers to the transition mode, where there needs to be a hidden SSID from, if a normal client without the support of OWE can still, use it, whereas then when a client that supports OWE will be kind of forwarded to that hidden BSSID. I don't think that that's, too much extra congestion. That would be my kind of answer to that. But it will be probably another SSID that gets broadcasted in a beacon, and of course there's you know, a little change in the utilization, the channel utilization, for instance, but I wouldn't say that that is significant impact. What do you think, Jim?
Yeah, it's something you definitely want to consider in high density areas. The extra overhead from the extra beacon if you're using OWE in transition mode. So just looking forward to the 6 gigahertz band, won't need, in fact, you may not be able to use the transition mode, so shouldn't be an issue there.
Yep.
Just a comment from Gary. He says, I think most open networks nowadays, in most open networks nowadays, encryption is done at the application layer. So they aren't as risky as they used to be. And I think that's right. Back in the days of Firesheep and unencrypted HTTP traffic, then open networks were a lot riskier than they are today.
Yeah.
And maybe one last question, Tuomas. This is from Anush, and he wants to know if WPA3 uses the 4-way handshake.
It does use the 4-way handshake. It's just how that pairwise master key gets created during that first authentication association part. But after that, it's followed by the 4-way handshake.
Cool. And actually, one last question. I forgot about this one. This came in from Gene, and the question is, this is a good one. Because protected management frames is mandatory with WPA3, then how can 802.11r fast transition be implemented? Are they compatible? That's interesting, because with WPA2, you could either use fast transition or protected management frames, but you couldn't combine them.
Yeah, I'm not sure if that's supported on when you have a WPA3 network and enabled the protected management frames. I'm not sure if it supports the FT or not.
Yeah, I think there's now a FT EAP, fast transition EAP method that was introduced with WPA3, but I think it's optional.
Yeah.
So I would expect, it'd be something to talk to your AP vendor about in terms of how they're implementing WPA3, because I still think that challenge may exist.
Yeah. Yeah, there are some caveats that you need to consider if you are going to move from WPA2 to WPA3.